This is a video about the scaling transform. Let me define a scale vector right here, s. This is a small s, and this is a vector which has three coordinates in each of the x, y, and z axes, namely x, s, x, x, s, y, and s, z. Now, what I want to use this scaling vector for is I want to scale an object in each of the axes by the specific coordinates set here. So I want to scale an object by factors of x, sx, sy, and sz in their respective axes. So a scaling matrix is used to enlarge or diminish an object. And to do that, we have to define a scaling matrix. A scaling matrix will use this vector s. We give this vector s, and it will look something like this. This is the scale matrix, and which magically appeared on the screen just now. So again, I'll just repeat one more time why we have a 4x4 matrix and with a 1 at the end and not a 3x3 matrix. We're going to use homogeneous coordinates, and if you don't know what a homogeneous coordinate is, please search it up, because all my videos are based on homogeneous coordinates and affine transformations. So this, let's just say if x, sx, sy, and sz were uniform, if they were the same number, it would be called a uniform transformation. And if they were all different numbers, or just one of them was different, then it would be a non-uniform transformation. And as you can see right here, all these three vectors, sx went on in this place in the matrix, as well as sy and sz. And if you just multiply this with, let's just say, a matrix or a vector which contains the coordinates points, the object's points, so let's just say the O is our object matrix. If you multiply these two together, this object should scale by these factors in each of the directions. And let me define the inverse of a scale matrix. The inverse of a scale matrix looks something like this. And this one's a little trickier than rotation and translation and whatnot. So this is the inverse of a scale matrix, where you want to diminish the objects by a factor of sx, sy, and sz in each of the coordinates. And I'd say for that's it for the inverse, but one shortcut, there's a little shortcut when it comes to scaling transformations. When you have a uniform case, only for a uniform case, you can do scale in a scale by this method. So now we know that our sx and sy and sz are all equal to each other. So we could actually do something like this. So I put a 1/5 here because I'm going to assume that we want to scale by a factor of 5. And so usually if you want to scale by a factor of 5, each of these would have been a 5, and this would have stayed as a 1 in the case of a uniform scale. But we can also define a uniform scale in this way. This might take a little bit more computer power, but it's easier to write, I guess. But why I'm writing it like this is because at all times an affine matrix with homogeneous coordinates, same thing, but this for the element 4, 4, fourth row and fourth column, should always be 1. And if, for example, your game engine sees that this thing is a 1/5 and all the other ones are 1, it's going to try and make this 5 by multiplying it by 5, but it's also going to multiply all the other coordinates in this space by that number. Hence, this matrix will actually turn out to be the same as 5, 5, 5, 1, and all these will be 0. And this is the form we're used to looking at from here, and this is just this guy right here as a shortcut way of doing it. Now I'm going to introduce you guys to something called a reflective or mirror matrix. And why this falls under the category of a scale matrix is because it uses the scale transform, and the rules you have to follow if you want to reflect your object or mirror your object is, one, if you have let's just say you have that scale vector S and you have the values, let's just say A, B, and C. If any two, let's start with the other case actually. If any one value or all three values, if one or three values are negative, then it is a reflective matrix. And what that means is that, for example, we have an object right here, and we have the z-axis as well, but the z aspect for this guy is just 0. So let's say if all three of them, or one of them was negative, one of these numbers was negative, then we could reflect it like this, where this and this would be the negatives of each other, and this would be the negative. Same with the other coordinates. So this is a reflection, and it can only happen if you have one or one or all of the coordinates negative. If you only have if you only have two coordinates that are negative, then this object will rotate by pi radians, which is 180 degrees. So if two are negative, then rotate, and it will rotate in the respective axis. I'm not going to give you a full out illustration of which axis because there's a lot of cases here, but all you have to know is that this is one of the cases where it's not a reflective matrix, and it will rotate in a certain axis. And why I'm teaching us this is that the reflective and mirror matrices are very important to game programming, because sometimes they can cause incorrect lighting. They could cause things to appear where they're not supposed to appear. And like, for example, if you wanted to scale something and you accidentally had some negatives in there, you might reflect it, you might rotate it, and you might not know what's going on. So these are the cases. So remember that scaling matrix we had, and then you had the Sx, Sy, Sz, 1, and all the other ones were 0. All the other ones were 0. And these ones, if these three coordinates right here corresponds to the A, B, and C. And another way of detecting, just by simple math, that if a matrix is a reflective matrix or not, is that we can compute the determinant of the upper left three elements. So for example, we have in the previous example, if we had a scale by 5, so for example, let's say the first one was a -5, the second one was 5, and the third one was 5 as well. This one's 1, and all the other ones are 0. To see if this is a reflective matrix or not, we can compute the determinant of this space right here, these 3 by 3 elements, so which would be -5 times 5 times 5 plus 0, because all the other ones are 0, plus another 0, minus 0, minus 0, minus 0. So this is the determinant, and this computes to be -5. negative 125. And if you get a negative product, then it is a reflective matrix. And for example, let's say, like I said over here, if you had two negatives, it's not a reflective matrix, and instead it rotates by 180 degrees. In this case, if you have two negatives, this would have been a negative, and the product would have been a positive. Hence, that would not be a reflective matrix. So that's it for this video about scaling matrices and their subset of reflective and mirror matrices. Please subscribe.